section 2.2, the limit of a function. Suppose f of x is defined when x is near the number a. Then we write the limit as x approaches a of f of x equals L if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a but not equal to a. So this is a more formal definition for what we were doing in the previous section. We're going to get an x value that's close to the x value that we want to be near, but we won't actually choose that x value. And then we'll take a look at this concept of a limit is what we approach to for our y value as those x values approach each other. So as an example, let's guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. So to do this, again, we'll make a table of values for x values that are near 1 but not equal to 1. So let's look at values that are smaller than 1 first. So for example, we could look at 0.5. When we plug in 0.5 for x on the top and bottom, we get 0.666666667 for f of x, assuming that we let this thing equal f of x. We're going to let just the x minus 1 over x squared part equal f of x. X minus 1 over x squared minus 1 part, not including the limit part. So just this thing is what equals f of x. Okay, so we plug in, we get 0.66667. If we plug in another x value, let's say 0.9, we'll get closer to 1. So hopefully we get closer to some y value that we can identify. We do this to look for pattern, just like we did previously. If we plug in 0.99, we get even closer to 1. Get 0.502, 513. If we plug in 0.999, then we get 0.5000250. And as you can see, we are reaching some sort of number, it seems, as we plug in values that are closer and closer to 1. So we have to be a little bit careful. We could say at this point the limit is probably 0.5, because it looks like the more 9s we add, the closer we get to 1, the closer we get to 0.5, because we get more zeros after the 5. But we should check to the right of x, and by the right I mean above the x value of 1. So if we look at some numbers that are bigger than 1, but still, kind of close to 1, we can build another table. So how about we look at, say, 1.5. Then when we plug 1.5 in for x, we get 0.00000. So that's a little bit far from 5, but it makes sense to be far from 0.5 at this point, because it's just like when we plugged in 0.5, it wasn't exactly 0.5 at that point. It was 0.66667 when we evaluated it. So let's get closer to 1. Plug in 1.1. We get 0.476190. So it looks like we are getting closer to 0.5. Let's just keep plugging in just in case. We get 0.499750 and one more. Yeah, that looks pretty close to 0.5. So it looks like regardless of whether we're below the x value of 1 or above the x value of 1, if we get really, really close to 1, we get really, really close to 0.5. So I think we can say with some authority at this point that the limit as x approaches 1 of x minus 1 over x squared minus 1 is 0.5. Let's do another example. Let's estimate the value of the limit of square root of t squared plus 9 minus 3 over t squared as t approaches 0. Again, we can make a table. All these t values that we'll have. And the t values will approach 0 this time instead of approaching 1. And then instead of x, I should use t. And we will call this guy f of t for shorthand. Okay, so let's plug in, let's say 1. Then we get 0.162277. Notice, however, that there's t squared in the top and bottom. So it doesn't matter if I plug in a minus value. It will have the exact same y value. This function is actually even in that sense. We can plug in negative x values and get the same exact f of x value, or in this case t value. So that means that we get the same 0.162277 regardless of whether the 1 is positive or negative. So that saves us a little time. We basically will have a table that's twice as big as it seems. And this also means that we're going above and below t equals 0 without having to make another table. So let's look at plus or minus 0.5. That'll be 0.165525. If I look at plus or minus 0.1, then that's 0.166620. Plus or minus 0.05 gives us 0.166655. And you could probably see where this is going now. This gives me 0.166666. So it seems like the limit of this function is square root of t squared plus 9 minus 3 over t squared as t approaches 0 is 0.166666, which is 1/6 if you keep the 6's repeating. Let's guess the value of the limit of sine of x over x as x approaches 0. So let's let this guy be f of x, the sine of x over x part. We can make a table. Again, it doesn't matter whether we're positive or negative, we're going to get the same f value. So we plug in some values, trying to get close to 0. Notice we don't start initially really close because we want to try to get an idea of how we're moving. It's good to have some perspective. So we go from 1 to 0.5 to 0.1. To 0.05. This is kind of like when they're baking in some cooking show and they put something in the oven and then they pull it right out. Movie magic. I just give you all these numbers that we plugged into a calculator without having to actually pull out the calculator. So it looks like the limit as x approaches 0 of sine of x over x is 1. Because if we just have enough 0.9999s, it's 1. This should intuitively make some sort of sense, because if I took a look at the graph of sine, wow, that was really bad. Not much better. Okay, so if I took a look at the graph of that, and I took a look at the graph of just x, which is just y equals x, I can compare these guys around 0. Let's zoom in over here. So if I look at just this part near 0, it's kind of like this, which is almost matching completely with the line y equals x. It's almost a straight line if you get close enough to 0. So it makes sense that the limiting value as we get sort of infinitely close to 0 would be the same as the limiting value of x over x, which is 1, intuitively. That's not like a rigorous proof or anything, but it's good to have a little intuition geometrically. Let's investigate the limit of sine pi over x as x approaches 0. So that's a little ominous to say investigate, but we are dutiful mathematicians. We will check it out. Let's see, what if we plug in 1? So f of 1 is the sine of pi, which is 0. If we get closer to 0, f of a half is the sine of 2 pi, which is 0. F of a third is the sine of 3 pi, which is 0. F of a fourth is the sine of 4 pi, which is 0. F of 0.1, 1/10, is the sine of 10 pi, which is 0. F of 0.01 is the sine of 100 pi, which is 0. So at this point, you're probably saying, okay, well, we're getting closer and closer to 0, and we're getting 0 every single time, so the limit should be 0. Okay, but here we're just wrong, because even though f of 1 over n is the sine of n pi, which is 0 for any integer n, we have other values like f of 2/5, which are 1, and f of 2 over 101, which is also 1. And in fact, there are infinitely many of these small values as we get closer and closer to 0 that give us a number other than 0, they give us 1. And in fact, there are infinitely many values that closer and closer to 0 that give us another number minus 1. So this kind of doesn't make any sense, but it could be helped a little bit if we can graph this thing, which is a big if, unfortunately, because of how bad I am at drawing these graphs. So if we start out over here, this is the sine of pi over x. It goes up and down and up and down and up and down and up and down and faster and faster and faster and faster and faster and faster. It goes infinitely fast up and down. Here's 1 and here's minus 1. Oscillating between minus 1 and 1. And then it does the exact same thing on the other side. So it doesn't matter whether you approach from the left or right, you will hit all of these little zeros. Let me see if I can show you that. So you could see that it does approach 0 in some sense, because it is hitting infinitely many zeros as you go through. Those are all of the values that we computed to begin with, the f of 1 over n guys. However, just as many zeros, there are 1s too. It hits 1, it hits 1, it hits 1, it hits 1, it hits 1 infinitely many times. And similarly, it hits minus 1 infinitely many times. So because it doesn't hit any specific value, it doesn't like hone in on 0, it doesn't hone in on 1 or minus 1, it oscillates between all three of those, we say that the limit does not exist. So the limit as x approaches 0 of sine of pi over x does not exist. And we will abbreviate this by writing DNE in the future, because this is going to come up a lot, these limits not existing. Okay, so let's do another example. How about the limit of x cubed plus cosine 5x over 10,000 as x approaches 0? So we can build a table. Again, we'll call this guy f of x. That's the whole thing, x cubed plus cosine 5x over 10,000. Alright, let's look at 1. So if we plug in 1, we get 1.000028. plug in 0.5 and get 0.124920. 0.1 gives us 0.001088. Plugging in 0.05 gives 0.000222. And then plugging in 0.01 gives 0.000101. So it looks like we're getting closer and closer to 0. So we could say that the limit as x approaches 0 of x cubed plus cosine 5x over 10,000 is 0. But then we'd be wrong again, because it turns out if we continue our table, it actually approaches a value other than 0. We just didn't make a table that was big enough, because if we plug in 0.005, we get 0.00109, and if we plug in 0.001, we get 0.00010000. So in fact, it looks like it approaches 0, but it actually stops right before 0, and instead approaches 0.0001, which is 1 over 10,000. This will also make a little bit more sense later on, because we'll see that the limit as x approaches 0 of cosine 5x is actually 1, which makes sense that this thing would then approach 1 over 10,000 because of the 10,000 in the denominator. But for now, the table is good enough, provided that we made it long enough. So this is one of the pitfalls of calculating limits by inspection. You have to be very careful looking at your tables, because sometimes if you don't choose enough values, you can get a very misleading result, as in the previous example, where you only choose 1 over n, or in this example, where you truncate your table too quickly. Okay, let's do another definition. We write the limit of f of x as x approaches a from the left equals L if we can make the values f of x arbitrarily close to L by taking x to be sufficiently close to a with x less than a. Similarly, if we require that x be greater than a, we write that the limit of f of x as x approaches a from the right is L. So this minus sign is not read as minus, it's read as left. And this plus sign is not read as plus, it's read as right. It's either the limit as x approaches a from the left, or the limit as x approaches a from the right. We just use a minus and a plus sign as shorthand. Let's investigate the limit as t approaches 0 of the Heaviside function h, defined by h of t equals 0 if t is less than 0, and 1 if t is greater than or equal to 0. So let's draw our Heaviside function, which, always looks intimidating because it's piecewise, but it actually isn't in this case. Here's t, here's y equals h of t. So it is 0 if t is less than 0. So it's 0 if t is less than 0. I drew an open circle because we're not including 0. And then it's 1 if t is greater than or equal to 0. Okay, so let's see. The limit as we approach 0, if we go in from this direction, we get closer and closer and closer to 0. Looks like we get, that y value of 1. But if we go in from the other direction, we get closer and closer and closer to 0. So it looks like we do not approach any specific value as t approaches 0 in general. So we could say that the limit as t approaches 0 of h of t does not exist. However, as we approach from the left, we do approach 0. We approach a specific value from that one direction, so we could say that the limit as t approaches 0 from the left of h of t is 0. Similarly, as we approach from the right, we approach a specific value of 1. So the limit as t approaches 0 from the right of h of t is equal to 1. We make the remark that in general, the limit as x approaches a of f of x equals L if and only if these left and right limits match. So that means that the limit as x approaches a from the left of f of x is equal to L, and the limit as x approaches a from the right is equal to L. So both the left and the right limits have to exist, and they have to be the same as each other, and then the limit in general will be forced to be that same limit. Let's use the graph of g to state the values, if they exist, of the following. First, the limit of g of x as x approaches 2 from the left. So we come in from the left. We can see that we are approaching, well, I should probably draw that higher. We're coming in from the left along g. We're going closer and closer and closer to 2. You can see that we're approaching the value of 3 from the left. So this thing equals 3. If we approach from the right, however, we trace this function along from the right. And as we approach 2, we get closer and closer to 1. So those limits do not match, so that means that the limit of g of x in general as x approaches 2 does not exist. If we look at approaching g of x, approaching 5 from the left, so then we're coming in all the way up until we get to 5, it looks like we approach 2. And if we go from the right, we also approach 2. So the limit as g of x as x approaches 5 of g of x in general must be 2, because the left and right limits were 2. This is interesting because if you look at g of x at 5, it actually equals 1. So in this case, the value of the function is not equal to the value of the limit, because remember, for the definition of our limit, it was the value that x approaches this a value, but not equal to a. So sometimes the function will be equal to its limit, and sometimes it will not. And sometimes it just won't exist in general. Let f be a function defined on both sides of a, except possibly at a itself. Then, the limit as x approaches a of f of x equals infinity means that the values of f of x can be made arbitrarily large by taking x sufficiently close to a, but not equal to a. Similarly, the limit of f of x as x approaches a equals minus infinity means that the values of f of x can be made arbitrarily large negative by taking x sufficiently close to a, but not equal to a. So what that means is that if we're approaching some x value, and the y value just gets insanely big, then we say the limit's infinity. If the y value gets insanely small, we say that the limit is negative infinity. We use this as a form of notation. We still have not said infinity is a number. We're just using this as a shorthand of saying that the y value gets really, 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 really big. That's all this means right now. So let's find the limit of 1 over x squared as x approaches 0, if it exists. So again, we'll make a table. We're letting this guy equal f of x. Let's look at plus or minus 1. So that's 1. Plus or minus 0.5, that's 4. At plus or minus 0.2, that's 25. Plus or minus 0.1, that's 100. At plus or minus 0.05, that's 400. At plus or minus 0.01, that's 10,000. And at plus or minus 0.001, that's 1,000,000. So you can see that as we get smaller and smaller with the x values, it does seem like f of x is getting bigger and bigger and bigger. This also makes sense if we look at the graph, which also makes it more obvious why I'm allowed to just do the plus or minuses because I can just save a lot of time because the square removes any negatives, and in the graph, everything is nice and positive. It's basically like we start with 1 over x roughly, and then instead of drawing in the third quadrant, I can draw the next part in the second quadrant because the square will make everything nice and positive. Obviously, it's not the exact same as 1 over x, but roughly with a picture, it's nice. Okay, so that means that this limit does not exist because the value of the function does not approach any specific value. It just goes and gets insanely big. So this limit, does not exist. That being said, the limit, the values of the function are becoming arbitrarily large positive. They are shooting all the way up in the air. So even though the limit doesn't exist, I could be a little bit more specific. And I could say that the way that the limit doesn't exist is that it equals infinity. This is kind of very confusing and bad notation because we write an equal sign, which implies the limit does exist, but the limit does not exist. This is just shorthand by saying it does not exist, and f gets really big. The reason it makes sense to talk about these limits not existing but equaling infinity and equaling minus infinity is that this characterization of non-existence actually gives us a little bit of information. So here we have a definition. The vertical line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. If either the limit is infinity, or the left-handed limit is infinity, or the right-handed limit is infinity, or any of them are minus infinity, then we get a vertical asymptote. So if any of these left-handed, right-handed, both two-sided limits, any of them are equal infinity or minus infinity, either they get really, really big or really, really small, then we get a vertical asymptote. So let's do an example. Let's find the limit of 2x over x minus 3 as x approaches 3 from the right, and the limit of 2x over x minus 3 as x approaches 3 from the left. So as x approaches 3 from the right, that means that we're going from like 5, 4, 3.5, 3.1, etc. We go values that are a little bit bigger than 3, but very close to 3. So the denominator of the fraction, x minus 3, becomes a very small number. Like 3.1 minus 3 gives you 0.1, etc. 3.01 gives you 0.01. That's a very small number, but it's still positive because we're to the right of 3. So it's a very small positive number. So then that tells us that 2x over x minus 3 will be a very large positive number, because when you divide by a small number, that makes it very big. Okay, so that means that the closer we get to 3, the larger positive this thing gets. So that means that the limit, I don't like the way I drew that, the limit as x approaches 3 from the right of 2x over x minus 3 equals infinity. Okay, so that means that we have a vertical asymptote at x equals 3, because we only need a single limit, left, right, wherever, to be infinity. But because the problem asks us to get it from the left, let's get that limit too. Pretty much the same reasoning applies. As x approaches 3 from the left, the bottom becomes a very small negative number. It's small like before because the difference would be very small, but it's negative this time because we're to the left of 3, so we have like something like 2.9 minus 3 or 2 minus 3, whatever. That gives you a negative number. So that means that, again, when we divide by a small number, we get a large number. So this would be a very large number, but because we have the negative, it would be a large negative number. So that means the limit as x approaches 3 from the left of 2x over x minus 3 is minus infinity. And this also makes sense if we take a look at the graph. We know that we have a vertical asymptote at x equals 3. These are the lines we drew before that we can never cross with the exponentials and logarithms. And it looks roughly something like that, where if you go from the right side, as you traverse along this function, you get huge. If you go from the left side, you also get huge, but you get huge negative. It goes down forever. So this is y equals 2x over x minus 3. Okay, lastly, let's find the vertical asymptotes of f of x equals tangent x. So we know that the tangent of x is equal to sine of x over cosine of x. So that means that if we want this thing to blow up, we want to see where there's an asymptote. We need the denominator to get closer and closer to 0. We want to get a very tiny denominator, because when we divide by a very tiny number, we get a very big number. So let's take a look really quick at the graph of cosine to see where that thing gets near 0. Okay, not my worst graph. Not good, but not my worst. So that's at pi over 2 for cosine. That's when it's 0. So as x approaches pi over 2, from the left, that means we're coming along here, it looks like cosine goes from positive to 0. So that tells us that cosine approaches 0 from the right. And as x approaches pi over 2 from the right, that tells us that cosine approaches 0 from the left, because to the right of pi over 2, we're going from negative values of cosine to 0. And we know that sine of x is positive near pi over 2. It's basically close to 1. So that means we have a positive number divided by, depending on the left or right direction. If it were going in from the left, it looks like cosine's coming in from positive, so that means that the whole thing is positive, so this thing blows up to positive infinity. So we have the limit as x approaches pi over 2 from the left of tangent of x equals infinity. And if we have pi over 2 being approached from the right, then that means that cosine is approaching 0 from the left, so those are from negative values, so that makes this thing large negative. Okay, so that means that x equals pi over 2 is a vertical asymptote. And similarly, we could use this exact same argument to say that x equals pi over 2 plus any multiple of pi, any integer multiple of pi, are vertical asymptotes. So we have to assume that n is some integer. So I say n is in z, the set of integers. And this also makes sense if we look at the graph. Let's put x and y. So we want an asymptote at pi over 2. So that's x equals pi over 2. And then we draw our nice tangent. So that makes sense. It's any integer multiple, so if we multiply by -1, makes sense we have an asymptote at minus pi over 2. And then for, let's see, our next tangent is 0 at pi, so with another asymptote at 3 pi over 2. And you can keep doing this forever. We have another asymptote at -3 pi over 2. All of the pi over 2 plus n pi's for integer multiples of pi.